This is a production of Cornell University.
All right, so we ended the last lecture on talking about what the fertilizers were. And we talked about all the different nutrients and things like that, and the sources of those nutrients for fertilizer. I think this is actually, I want to talk about how we make decisions about nutrient management, fertility management. I'm going to be coming mostly from the front end, i.e. How we deal with amendments. But when you start talking about nutrient management and fertility management, you also have to start talking about waste. Okay, and I mean waste not in the sort of traditional sense, you know, it's stuff leaving the site, but i.e. Actually, that's what I mean. I do mean actually stuff leaving the site. Usually when you start talking about waste, nutrient management, there's the connotation that you're just talking about one component of the nutrient cycle on your farm or your pot or whatever it is. Today, what I want to talk about up front, I'm going to start talking about how we bring stuff in, but I also want you guys to think about, you know, once it's in the system, whatever that system is, what's going to happen to it within that system. Because you have to consider, I mean, literally the last slide I have for today's lecture is the nutrient cycle, is the nitrogen nutrient cycle. Okay? Because when you're thinking about fertilizer and fertility and nutrients and how you're managing your field or your pot or your garden or whatever it happens to be, you have to think about the whole system. But generally we don't. Generally we think about, well, I need to get this amount of fertilizer on my farm. I'm going to add this. Okay? Does that make sense? All right. So how do we make decisions about fertility management? Well, hey man, I thought it's, nope, okay, this is right. Okay, well, generally, we need to make decisions about our fertilizer needs, our nutrient needs, okay? And we diagnose this by a number of different procedures. The first one, and most of us do this, we look at our plants and we look at how they're behaving and we sort of make an educated guess. Now, this can be coming from experience. Many of the farmers, many of the greenhouse operators, many of the gardeners, they've had this plant in the ground for a while, and they see these types of responses, and they know what they need to do, and they've done it this way in the past, okay, and they've had success, okay? Now, often this is based on either visual observation, visual diagnostic features. Some of these can be fairly ambiguous, but we look at what's going on our field or pot or whatever, and we make decisions based on that, okay? We also can basically make decisions based on analysis of soil samples. We take the soil that the plants are growing in or will be growing in, and we do analysis of it to give us an idea about how much nutrients are in that system, okay? We also can analyze the plants themselves. We can take tissue samples. We take these tissue samples, we send them to the lab, we get an estimation of we get an analysis of how much nutrients are in these plants or this type of tissue, if it's a leaf or root or whatever it happens to be. And based upon that, we can see where the deficiencies are, and then we can make decisions about what type of nutrients need to go into the system so that the plants can take them up. We also have nutrient response trials. Okay, well, I've talked a little bit about these before, but basically this is where this is why Cornell and many of the land grants have lots of farms across the entire state, okay, or whatever state they're in. Okay, the idea here is we look at a diversity of different crops, a diversity of different soils, a diversity of different climates, and then we basically lay out those plants and we trial them, and we provide different levels of nutrients or whatever happens to be the question for management, and we see how they perform. So we then use that information to make recommendations for future use or for future management. Does that make sense to everybody? Okay. Now, we're going to be talking about nutrients. So how, in fact, do we determine how much nutrients are needed for plants? Okay. Again, we can do that educated guess type of thing. Well, you know, I give it a little bit of this and I get this kind of response. Okay? Well, we could do that, but we actually could measure those responses. This is the field trial, back to the field trial. We can measure those responses. Okay? So here is a response curve looking at yield and then the amount of nutrients that are added. okay, of X type. It could be nitrogen, phosphorus, whatever it happens to be. You then plot your plant's response to it. Okay? If you have a positive response, you're basically looking at a soil that's deficient. At some point, when you start getting a negative response, you're getting up to levels that are toxic. But if you get this positive response, you definitely have a deficient soil. Okay? Now, if you do the same thing and you don't get a response, it's basically a flat line, and then if at higher levels you start seeing this dropping down, so you're seeing the toxic effect at this end, you're basically looking at a soil that is non-deficit. In essence, you're looking at this part of the curve on your soil. Does that make sense? Yeah? Okay. The last thing, and this has a lot to do with how, this is how we make determinations about how much nutrients we eat, but a lot of this has to do with this response curve. Okay? The last sort of thing that we think about when we're trying to determine how much fertilizer we use is we think about the yield expectations. Okay? How much yield we're going to be getting for the fertilizer. And the take-home point here is it's very rarely the maximum yield. It's usually what we call the optimum yield. Okay, has anybody ever heard this term before? Have you guys talked about this in like field crops and stuff like that where we're looking at response curves? Okay, so if this is we can use that as my response curve. Okay, so this is yield over here, and this is concentration of whatever fertilizer, whatever nutrient it is. Okay, now I'm going to give nutrients to a certain amount right here, and I'm going to get some sort of response. Okay, and if I keep doing this, I'm going to get a response that looks something like this. And then sooner or later, I'm going to get some sort of toxic, potentially, if it's potassium or something like that, it's going to keep going straight. Okay? But think about this. My maximum yield is right here. Right? So about this much fertilizer, nutrient. But look at this curve. The flat end of my curve, or I should say the steep, let's start with the front end. The steep part of this curve is actually from here to here. So for the amount of fertilizer that I'm getting, I'm putting in this field, the nutrients that I'm putting in this field, I'm getting a dramatic response. From here to here, I'm not really getting that much. So it turns out that optimum yield is actually right around here. For every dollar I put into fertilizer, I'm getting two pounds of whatever, okay? Out here, for every dollar I put in, because every one of these spots, every incremental increase in my fertilizer, that's more money. But I'm getting a very small response for this amount of money. So let's say this was $10 here. It took me $10 to get to here, and this is probably about another $10 to get to here. For my first $10, look at the response that I got. For my second $10, look at the response I got. Maximum, optimum. Make sense? All right. So my rate of fertilizer added, or how I determine, is going to be based on this sort of educated guess, my experience, okay, these measured responses, and my yield expectations. All right, so how do we find what's actually in the soil? How do we do this soil testing? Okay, well, we need to figure out the test has to be a measurement of availability. Okay, and the test must be fairly fast. Okay, because if it's not fast, it takes me a couple of years to get the data or a couple of months to get the data. My plant has already lived through that life cycle. Okay, it needs to be fairly inexpensive. If these tests are expensive, the farmers aren't going to be able to use them. Okay? It also needs to be fairly simple. It can't be some sort of complex thing that you have to do in the farm to get a response, to get another piece of information, to get another piece of information. It's basically got to be a very simple test. And finally, and this is perhaps the most important, it has to be correlated to the plant response. If it's not going to show you what the plant's going to do, it's not really going to be a worthwhile test. Make sense? Okay? And it's not just issues of deficiency, but it also is issues of toxicity. Remember what that response curve is. Right now we have successful soil tests for phosphate, basically potassium, zinc. We have acidity tests very well and salinity tests. Simple tests for nitrogen and sulfur are a little problematic. Sulfur is actually not that bad. Nitrogen, we can test for nitrogen. But the question here is it's not necessarily the simplicity of the test, it's the response of the nitrogen that's in the soil. We've talked about this, right? Okay. When we talked about this, we don't do these things when we're talking about this in the lab. Why don't we have successful tests for nitrogen? It's not that we don't, but the data from the test is pretty hokey. Why? You, yeah.
Because the fluctuations happen so quickly that it doesn't give you a good number.
Yeah, I take a test today, tomorrow the nitrogen levels can be totally different. Yeah, the test is really simple, but it's pretty meaningless. Okay, and that goes back to this component of what the test has to be able to do. All right, so all these tests extract some part, actually in some cases they do total analysis, but all these soil tests basically extract some part of the soil's total supply of element. Okay? These tests have to reflect the plant's ability to get the nutrient out. Just because the nutrient is in the soil doesn't necessarily mean the plant can get it. Does that make sense? Okay, so look at this graphic for a second. We're going to look at phosphorus. Okay? Imagine this larger circle represents the total pool of phosphorus that's in the soil. Okay? This smaller circle, this little with dots in here, basically represents of this large pool, how much of that pool is actually available and what kind. Okay? Phosphorus is a really good example. Okay? If this was a low pH soil, this total P pool was in a low pH soil, the vast majority of this phosphorus would be associated with iron and aluminum, and it wouldn't be available for the plants, right? A very small part of that phosphorus pool would in fact be available. Does that make sense? Yeah? Okay, so my test can't reflect how much phosphorus total pool. It has to reflect, or not reflect, it has to diagnose just the part of the pool that is available to the plants. So if I have a test like B here that doesn't actually test that available pool, it's pretty unsuccessful as a test to tell me what's going to happen to the plants, right? A successful test is going to be looking at this available phosphorus pool. Does that make sense? Now, one other consideration, and we talked about this when we were doing soil testing or soil sample collection when we were going out to Dillman Hill, but we also did when we were doing the soil mapping exercise. Soil sampling, you've got to sample your soils so that they actually represent what your plants are going to be in. Okay? Remember when we were at Dillman, we took the bucket out there and you guys took lots of samples, threw them in the bucket, mixed them up, and then pulled it out. Okay? What we were trying to do is get a representative sample of the management unit that you guys were, or the people at Dillman were growing the crops, right? If I had taken one individual sample, that sample perhaps, probably, would not have reflected the entire unit. You guys remember that we had that little blackboard exercise, and I drew a picture of the map, and I said, okay, well, you know, if I take one sample of this field, does it really represent the diversity of this field? Probably not. Now, the reality is when I start doing multiple samples, collecting multiple samples and throwing them in the bucket, not any one of those single samples probably doesn't reflect the entire nature of the field. But when I throw them all together and take a sample out, I'm getting the average of that field, in essence, sort of the average of that field. Now, the reality is I could have stuff that's really low. I mean, the fluctuation of characteristics of that field could be pretty dramatic. But the reality is I'm going to be managing that field pretty much as one single unit. And that's why we think about this. Your sample point is, or your sample that you're sending in for analysis really needs to reflect the characteristics of the field and how you're going to be managing it. And that's why we recommend doing these composite samples. All right. Screen's not advancing. There we go. All right. Now, one other thing to think about when we actually talk about soil testing, there are a lot of different landscapes, biomes across the world. Okay? One test for nitrogen or phosphorus or whatever it happens to be isn't necessarily going to work for all different regions across the world. So you need to have a test that's calibrated for your type of landscape. Now around here we basically use Morgan's testing for our nutrient availability. Mehlich is another option. Okay? These tests, these are just people's names that they've given them to their tests. These tests are basically used for different extractions of different types of soils. Okay? Your tests, these tests need to reflect the regionality of where you're taking your tests from. Okay? But they also need to be calibrated locally. This goes back to the land grants and these farms that are all over the state. They need to test these tests locally so that the test reflects the characteristics of that local environment. Does that make sense? And we're calibrating it based on some yield. Okay, here you've seen this. This is basically that drawing over here. Here is phosphorus for wheat yield. My yield increases. We find that critical value. This is optimum versus coming out over here, which is maximum yield. Okay, go. That's actually a good question. The question was, if you're using different tests across the country or across the world, how do you in fact compare the same test, the two different tests on the same plot, and they compare them? And what they do, the idea is to basically figure out which is the best test for that area to get the interpretations. You can certainly imagine if I have a more acidic soil versus a less acidic soil that certain tests would be better. Okay, you can certainly imagine if I have more different types of textures, activity, cation exchange capacity. If I have a high activity clay versus a low activity clay, you can certainly imagine those types of characteristics will. How do you, so the question was, how do you know which one is better? The tests themselves aren't better than the other. I mean, you can talk about the waste products and things like that. But the way we make the decision about which is better is basically on the plant's response to those tests. Okay, so around here we tend to like to use Morgan's more than Mehlich. Now you go to Pennsylvania, they tend to use Mehlich more. And the reality is that our soils, in the southern tier is pretty much the same as the northern tier of Pennsylvania, southern tier of New York. But if you look at the entire expanse of New York State, the response, the plant response to the test is better with the Morgan's than it is with the Mehlich. So that's the decision that we make. It's more reflective of a plant's ability to extract the nutrients than the Mehlich, at least in New York. Does that make sense to everybody? Yeah-ish. Okay. So I need a test. Okay, I have two different landscapes. Okay, and they have different soil characteristics, right? Okay, you can certainly imagine that different tests are going to reflect different amounts of nutrients that are extracted by the test. Okay, these tests are not a total digestion. They're trying to reflect the plant's ability to extract nutrients. Okay, so if I have a landscape here that has different soil textures, different pHs than the landscape over here, the plant's ability to extract those nutrients are going to be different in these two locations. Okay, we want to have a test that is reflective of that plant's ability. So New York State, Morgan's happens to be the better test to reflect that plant's ability to take nutrients out. Pennsylvania, the people in Pennsylvania feel that the Mehlich is. Okay? Now, if you start moving more into the Midwest, you're going to see much more of the Mehlich. If you start moving more into the Northeast, you're going to see much more of the Morgan. Make sense? It just happens to be the Midwest is different than the Northeast. Okay. So this slide makes sense to everybody? All right.
This has been a production of Cornell University, on the web at cornell.edu.